Okay, so let's now recap what we have seen and hopefully do better. Right? So we have seen basically a few basics of what a recursive function is like. So recursion means that you have a function that calls itself. A for loop, a while loop is not recursive. You can have any code in your function except if at some point your function calls itself, the function will stop at that point and go and compute the output of the function, which happens to be itself. And when that function ends, it will resume from where it's left off. So if you have a recursive function, you have to design it in such a way that it eventually will end. So generally the way you design a recursive function is that you have something you are keeping track of, like the n in power. N was decreasing every single time I called. So you have to then decide what is the condition that it should reach. So you generally think about your recursion as the basis, which is when should recursion end? This is generally the smallest condition you can think of. Often you think of the simplest possible case for which you have a single solution. For example, power 2 of 0 is 1, right? So this is good. That means that's a small condition I don't have to compute. So that can be my stopping condition. So this is a simple condition that requires no computation. So for example, if you are computing, like we said, power of 2, I know that 2 to the 0 is 1, so 0 is basis. Okay. So generally you have kind of some basic condition for which you know when the program should end. Then you have the iterative condition, which is basically figuring out how do you combine the solution for a smaller version of the function with the current one. So this is called the recursive step. So for example, if you are computing it for how do you combine solution for a simpler case to a true solution. Okay. This will become obvious as we do some more examples. Now, here's a little bit, one more philosophical statement here. Recursion is how you really define mathematics. A lot of the math that you know, number theory is based on recursion. All of logic is based on recursion. I did my PhD in logic, so to me, recursion, logic, computer science are all the same thing. So in a very philosophical way, they are all the same. Okay? So, and we try to teach you this as a kind of way of seeing that there is a deep connection between them. In fact, all languages that we speak are recursive. So English, French, whatever language you speak, Turkish, they all have recursive structures in them. In fact, there is a big conversation among linguists if it is possible to have a human language without recursion. So what I mean by that is, for example, when you report speech, A told B that, C saw something that, this is all recursive way of talking, right? You're building from simpler statements more and more complex statements. Okay? But using recursion to solve all problems is not a good idea. Recursion is good for some things, and it will take you some time to figure out what they are. So we will see some examples so you grasp the idea, but please don't use recursion as a way to solve everything, because it is really not the best way to do so, and I'll try to explain why. So let's write a very simple example, okay? And then we are going to see some other examples, and then we will talk about that. And I'm going to write this in a slightly different way, in the same way that I wrote the other one. Okay. So I'm going to use, again, an editor and a terminal, just so that you kind of get used to that way of writing programs. So let's write this function called blast of n. Okay. And I'm going to think about what my stopping condition is. Let's say this one is kind of not a meaningful function, but let's try this simpler. So let's say if n is equal to 0, I am going to print blast of. Okay? So this is my basis condition. So that means for any given n, if n is greater than 0, I want to increase it slowly so that it actually reaches n in my recursive step. So this is my basis step. And in fact, to make this even simpler, let's do this one. Okay. If n is greater than 0, I am going to print n, and then I am going to blast n minus 1. Okay. Now this is a function that doesn't do anything, it just prints something. And then I'm going to call blast of 5. So let's see what's going to happen. If I have blast of 5, the first thing blast of 5 will do is what? So blast of 5 is n is less than or equal to 0? No. So it's going to go to else, and it's going to print 5. Okay, so the first thing I will have is it's going to print 5. It's going to print 5, and then it's going to call blast of 4, right? So blast of 5 is still here, but now it's going to call blast of 4. For blast of 4, now 4 is on top of the stack. Blast of 4 is going to do what? Print 4, and then it's going to call blast of 3, which is going to print 3, and it's going to call blast of 2, which is going to print 2 and call blast of 1. Blast of 1 is going to print 1, and it's going to call blast of 0. And for 0, I'm going to print blast of, right? So I have printed 5, 4, 3, 2, 1, and blast off. Now, when I print blast off, this function is completed, so it will finish. I'm going to pop it off the stack, and I'm going to print the next one. I pop it off the stack until all of them, because there's really nothing else left after this point, right? So there's nothing else for the function to do. So that's what it does. Okay, so now let's play with this a little bit. Okay, I want you to think for a second, but don't tell me. What will be the output of this one? Just work it out. Think for a second. What will be the output of this slightly different function? Okay, so let's do the same. But I'm going to have the stack, and I'm going to have the output. Okay, so the first thing that I call is blast of 5. And what does blast of 5 do? It calls blast of 4 before it prints, right? Which then calls blast of 3. Again, it calls before it prints. It calls right here. Then blast of 2, blast of 1, and blast of 0. Now blast of 0 prints blast off. Now that's popped from the queue. Now I am in blast 1, but I'm right in this part. So I'm going to print 1. This one is done. Now I have blast of 2. I'm here, print 2. This one is done. Now blast 2 is done, so now I'm here at blast of 3. So I'm going to print 3, 4, and 5. Okay. All right, one final one. How about this one? So you print 5, 4, 3, 2, 1, blast off, and then 1, 2, 3, 4, 5. It combines both of them. Okay, let's try another one. Try this. Take a few minutes and work this off on paper, and then we are going to start writing more complex functions. All right, let's try that one. This is pretty awful, but I will do my best. Okay. So let's do RP1 of L and 0, right? So we will do the same. I will have stack here, and I will have the output here. So in the bottom of my stack, I have RP1 of L of 0. And the first thing that I look when I get this is so when I call L is this list and I is 0. So is I less than the length of L? Yes, 0 is less than the length of L. So I'm going to print L of I. That means I'm going to print L of 0, which happens to be 2. And there is a small comma right after, right? So there's a comma here. That means the next thing I'm going to print right next to it, not into the next line. And then I'm going to call RP1 of L of I plus 1. So I'm going to call RP1 of L of 1. So when I come here, it's going to print the first item, which is 3. And it's going to call RP1 of L of 2. It's going to print it into the same. And 2 is less than, so it's going to print 5. And RP1 of L of 3. 3 is still less than the length, so it is going to print 7, which is going to be RP1 of L of 4. And then 0, 1, 2, 3, 4, so I'm going to print 11. Then I'm going to call RP1 of L of 5. Now, this is no longer true, because 5 is not less than the length of L. Length of L is 5. So, as this is false, I'm going to implement this, print, and at this point, this function ends, right? This L of 5 will simply do a print, meaning that it will do a new line, and then this will end. When this function ends, remember there's nothing else in this function, so this one will end, this one will end, this one will end, this one will end, and this one will end. All right, so this is what RP1 will do. All right, let's see what RP2 will do. So we have the same thing. You have L of 2, 3, 5, 7, and 11. So we have output and stack. And I now start with RP2 of L of 0. So this is the same logic, except it will call immediately RP2 of L of 1, RP2 of L of 2, RP2 of L of 3, RP2 of L of 4, and RP2 of L of 5. When it comes to L of 5, this if statement is not correct, right? So it will actually print a new line. So it will actually print a new line. And then this one will be popped off the stack. Then now I'm going to print the L of I. So I'm going to print L of 4. So L of 4 is actually 11. So I'm going to print 11. And this will pop. Then I'm going to print 7. This will pop. Then I'm going to print 5, 3, and 2. Now the important thing to remember here is that even though I've printed roughly the same, there's actually one new line here, and when I'm finished, I'm at the end of this line. I haven't printed a new line, right? Because there's a comma at the end of each one. So there's a space and a comma, but if I were to print something, I would print it on the same line as this one. Okay? So does this kind of make sense in a way? So you had two different kinds of recursion. I mean, they are the same, but I defined it in a slightly different way. In one where I started from a big number, like the power of n, and then I kept going slower, n minus 1, until I know that if I started from a positive number, n is eventually going to reach 0. Whereas in this one, I started from 0, but then I kept increasing I until I reached the length of the list. So either way is fine, as long as you know that eventually you are going to reach this one condition, right? Here the basis condition is this, because this is the condition that ends my recursion. And here, this is my basis condition, which is the one end my recursion. Either way is fine, as long as my recursive call goes towards it. Okay? So now let's try to think about what the recursive condition can be. So this is where we talk about kind of the math version of this. So we start with math problems, but then you will see that it's far more reaching than math. So let's try, for example, power. So I wanted to compute 2 to the n, or I call this power 2 of n. Okay? So if I wanted to define power 2 of n, I want to define it as a function of two things. What if I knew the solution to power 2 of n minus 1 somehow? If I knew power 2 of n minus 1, to compute the power of n, what do I do? So if I were to say 2 to the power of n is 2 to the power of n minus 1, and then times 2, right? It looks easy, but it gets complicated. Okay? So this is power of n minus 1. This is power of 2. So I can compute this. Okay? So what I did is I defined the problem, power to the n, as a function of power n minus 1. So if I start with n, I'm going to decrease n by 1 at every step. And eventually, I have to reach a condition that will stop me. What will that condition be, we said? So since let's say if it's positive, it goes down. So it's either 1 or 2 or 0. Okay? Which one is a better condition? So do I want to stop at 2 or 1 or 0? Is 2 to the power 0 defined? Yes. Is 2 to the power 1 defined? So maybe I want to use the thing that is the smallest value for which it is defined, right? So which is 2 to the power 0. But now I have to mentally check. Okay, so what is, so power 2 of 0 is 1. Now I want to check whether in fact power 2 to the 1 is correct. So if that is the case, power 2 of 1 will be, this is 1. 1 times 2 is 2. And 2 to the 1 is 2. So it is correct, right? So I do a mental check to see if I do the next one correctly. And from then on, it's going to increase and correctly compute the result. Okay? So here's another one that is also a very common first example, is factorial. Okay? So n factorial is 1 times 2 times 3 times all the way up to n minus 1 times n. Everybody knows about factorial? Okay. All right. Is 0 factorial defined? 1. Okay, so keep that in mind. I'm not going to put 0 there, but keep that in mind. Okay, so well, you can look at this and you can say that this is n factorial. What is this one? This is n minus 1 factorial. So I can define n factorial as n minus 1 factorial times n. So that means if I start from n, I can go down by 1 until I reach the smallest value, which in this case is going to be what? Do we want to define it as 1 factorial or 0 factorial? Let's define it as 1 factorial. So let's say 1 factorial is 1. And then you can decide whether that's okay or not. So let's write this one down. Okay. So now we are going to write a different one. Factorial of n. Now you can write recursion in any way you like, but I like to write my first ending condition first, and then recursive condition next. It's a kind of mental awareness of what I'm doing. So the first condition is not recursive. If n is equal to 1, then what is my output? What is the output then? What is 1 factorial is? 1. Thank you. All right. It is boring, but I will try to do something exciting soon. Okay. If it is greater than 1, right, this is just what we mean. If else it's greater than 1, so then I'm going to find factorial of n minus 1, right, whatever it is. Then I'm going to return x times n. Find the factorial of n minus 1, multiply that by n, and return it. If you get really comfortable with this, instead of writing it like this, you can also just write like this. Okay? So recursive functions have the property of being very short, but at the same time very, very hard to debug. So let's go back to this. That's better, right? So find factorial of n minus 1, return x. And then let's write simple program. Okay. So let's do this. So 3 factorial should be 1 times 2 times 3, 6. 4 factorial should be 6 times 4, 24. 5 is 120. 6 is 720. Let's do 20. Some very large number, and it gets bigger and bigger. Okay, so what will happen if I enter a negative number? I will do it for you. I don't know if the int actually fails. What does it say? Maximum recursion depth reached, which is what we call it? Stack overflow. That's right. So what happened is that it started with n minus 1, right? So it was negative 1. So it tried to find the solution to negative 2, to negative 3. It kept popping stuff on top of the stack. And will it ever end? No, because I'm trying to reach n is equal to 1. It will never reach, right? Because I'm continuously subtracting. So you can see that it printed this for a long time. And then eventually said, that Stack Overflow has reached, right? This is how many things were in the stack, and as it popped everyone, it complained to me. It was kind of unhappy, right? So this is the same thing you will see in Wing. Let's see how it looks in Wing, just so that you can see. Okay. So let's do the same so you can see what that looks like. Okay. So this is the thing. And then let's do -1. And it will give you a similar error, right? So this is what we call Stack Overflow. Because you actually keep recursively calling, but the recursion never ends. Now, one of the important things to remember is that as you become comfortable with writing recursion, you will think that recursion is a good solution for everything. But in fact, this is not true. Many problems can be written without recursion. And in fact, recursion is actually inherently more costly. Why is it costly? Because you have the cost of putting something in a stack, popping something from the stack. If you could do the same thing with a for loop, you could do it. Can you compute factorial with a for loop? Of course, right? It's just a single for loop. You don't need recursion to do that. You should never really write this. So obviously, if you wanted to have iterative version of factorial, you would say for I in x range of, well, you can just say range of n, it should include n plus 1, something like this, right? So you should never really use recursion for that. In fact, so I'm going to write another recursive function, which is in fact, you should never implement recursion for this. But I will do it because it's so simple to write recursively. And then you're going to tell me why this is a bad idea. So, Fibonacci series. Anytime I ask your TAs, give me an example question for recursion, they say Fibonacci, because this is what we always do. So the Fibonacci numbers, the first number is 0, the second number is 1, and then the third number is the sum of the previous two numbers, right? So basically it's this simple idea. So you have 0 and 1. So this is the Fibonacci of 0, this is the Fibonacci of 1. And then Fibonacci of 2 is the sum of these two, which is 1. Fibonacci of 3 is the sum of these two, which is 2. Fibonacci of 4 is the sum of these two, that is 3. Okay? And the sum of these two is 5, and so on. So you can create a sequence by continuously adding that Fibonacci of n is Fibonacci of n plus n minus 1 plus f of n minus 2. And you need basically two conditions, right? When n is equal to 0, it is 0. When n is equal to 1, it is 1. Right? So there are two ending conditions. And for everything else, you can compute it based on the Fibonacci of the other two. So we can write this. So if n is equal to 0, I want to return 0. If n is equal to 1, I'm going to return 1. Else, I'm going to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay. So if you want to see how that looks, Okay. So let's write a simple piece of code to see if this function produces the same output that I just said it would. So parentheses. Oh, yes, thank you. And yeah, it's going to start from 0. So let's see. Okay. Does that look correct? Now, why is this a terrible idea to write this function this way? This is a terrible, terrible thing to write. Why is that the case? Yes? And that is bad because? That is true. It is extremely inefficient because it keeps calling itself. It does something even worse. Because of that, it computes the same thing over and over and over again. To compute the Fibonacci of 5, I compute the Fibonacci of 4 and 3, right? To compute the Fibonacci of 4, I compute again from scratch Fibonacci of 2 and 3. But I already knew Fibonacci of 3, right? So why do I do this? If you actually did from the beginning, you can keep remembering the values you computed and just add them, instead of computing them from scratch. Every single one, I'm computing a huge, like you said, massive recursive call, which is totally unnecessary. In fact, when you take a course in programming languages, you learn about what kinds of recursion are good, what kinds of recursion are bad, tail recursion, so you will see all of that. But this is bad, especially exactly what you said. You have 2 recursive calls. That seems bad. Okay, so now what I try to do is, at this point, and your next lab is going to be on recursion, I will try to give you 2 examples where recursion is natural. Okay? So there are many examples where you can do recursively, but it is not very natural to do it recursively, or that you really should not do it, even if it looks good, right? Sometimes I hear like this, student comes to CS1 and I solved it using recursion. It's like, it's not like necessarily great, right? It's just recursion is not like the solution to everything. So, like I said, under Piazza, you will have 2 functions. And we are going to use already given functions. Like in a cooking show, I'm not going to write the whole function. But we've already done both of them more or less. So if you go under resources, we have 2 functions. One is called merge sort. The other one is called Sierpinski. Okay? Take these 2 functions, and then we are going to write 2. And then if we have time, we may do one more, but I don't think we will. So let's start with merge sort. Okay? This is actually stuff we have done in class. Remember that when we did sorting, we basically had a way to time functions, and then we wrote this merge sort algorithm, which basically I renamed as merge sort iterative. This is from course notes. So what this function does is it takes a list, it creates a list of lists. Remember this? So the idea was that so suppose I wanted to sort 5, 4, 3, 1. The first thing that I did was I created first a singleton list. Like this. Then I took pairs of lists and then I merged them. So I basically merged them in sorted order. So this would have been 4, 5, and this would have been 1, 3. Then I took again pairs of lists and I merged them. So I had 1, 3, 4, and 5. And when I was done, there was only one list left. Then I popped that list, and then I returned that, and my merge sort was done. Do we remember this? Okay, kind of. Well, you have to for final. So the point is that this algorithm had 2 steps. One was for managing these lists, which was the merge sort, and then one function that took two lists and then merged them, assuming these two lists were in sorted order. Okay, so that was merge. And so this is the merge function. We have done this in class. And this is the merge sort function, which basically creates this list of lists and then does this part. Okay, and then we can look at how long this takes. Merge sort was, even though it has the same complexity as the internal sort, it was, you know, somewhat slower because the internal sort is compiled, written in C++. Okay, so I want to now write the same function, the merge sort, but using recursion. So, and I'm going to call it merge sort recursive of L. Okay. Again, let's think about what would be my ending condition. What is the smallest thing that I know is sorted? List of one item is sorted already. I don't need to sort it again. And list of 0 is already sorted, right? So let's do that. And I'm going to write this in the most efficient way I can. So I'm going to look up the number of items once. And if number of items is greater than or equal to 1, I'm going to return L, meaning that list is already sorted, right? So I don't need to do anything else. List is sorted. If the list is not sorted, then what I'm going to do is I'm going to take the list, divide it into left and right. Okay, just divide it in half. And I say, okay, first sort the left half, then sort the right half. Okay, by using merge sort. So let's find the midpoint, which is number of items divided 2. This is the midpoint of the list. And recursively merge sort the first half of the list, and then second half of the list. Do you remember slicing? Right? Take the list, slice up to mid, and from mid to the end. Okay? So somehow, think about this in list of 2 items. If you had list of 2 items, when I divide it by half, I'm going to have 2 singleton items. So merge sort is going to return this one and this one. So when I get these 2 lists, they are already sorted if I have 2 items. So what do I do with these lists of 1 items? So basically, what I will have is, suppose my initial list was 4 and 3. Okay? So I'm going to divide this into 2. One is going to be a list of 4. The other one is going to be a list of 3. Okay? Now I'm going to call merge sort this and merge sort this. So since merge sorting of 1 item is already sorted, this is going to return 4. And this is going to return 3. What is the next step? Next step, I need to merge them, right? Merge them in sorted order so that I will get 3 and 4. So I'm going to write that. I'm going to say merge L1 and L2 and return the list. Let's see if actually that works, and then we will see why it works. Okay, so let's see what happens when I do this. It does not work. Say it again. Yes, you're right. I was going to say, thank you. Try in different orders. Let's say, make sure that this is not a fluke. How about if I have randomly more numbers? Right? Feels like magic, right? So what happens? So let's try again. Now with a bigger list. This time, let's say I have merge list of 4, 3, 5, 2, 1, and 6. Okay? And I'm going to just say merge sort, right? So what this will do is it will recursively call merge sort of the first half, merge sort of 4, 3, and 5, and merge sort of 2, 1, and 6. So now my stack is going this way, right? So this is the bottom of stack. So now merge sort of 4, 3, and 5 is actually going to call merge sort of 4 and 3 and merge sort of 5. And this one is actually going to call merge sort of 4 and merge sort of 3. Okay, I'm not even starting to process that one. So when this one finishes, so these two, they will finish. This will return 4, this will return 3. I'm going to merge them, so I'm going to actually find 3 and 4. Then this function will return 3 and 4. Then I'm going to take 3 and 4 and merge it with 5, which I will find 3, 4, and 5 because of the merge, right? Then this function will return 3, 4, and 5. Okay. Now this function has finished. Now I'm going to look at this one, because this one will also call merge sort of 2 and 1 and merge sort of 6. This one will again now call merge sort of 2 and merge sort of 1. Now this will return 2. This will return 1. Now I'm going to merge them to 1, 2. So this part is going to return 1, 2. This will return 6. So I'm going to merge 6 with 1, 2. 1, 2, and 6. So this part is going to return 1, 2, and 6. Now finally, these two have finished. I got 3, 4, 5, and 1, 2, and 6. Now I'm going to do the final merge to get 1, 2, 3, 4, 5, and 6. So it's the same thing that I was doing, because I am always dividing it by half and then merging the halves to get bigger and bigger things, but I'm doing that recursively. And look at how short this function is. In fact, let's look at how complex it is. Let's look at the complexity of this. Okay, and I'm going to add a couple of zeros here just to see how fast that runs. Okay. In fact, it's actually cheaper because I don't have to maintain this bigger list of lists. I don't need to put them in a list of lists and then read from a list of lists, so it's actually a slightly less overload. So in fact, the recursive definition for this one is better than the iterative one, but this is not true for every possible thing. So do not go yet. I'm going to stop the recording because this is going to interfere